Bismillahirrahmanirrahim. So today we will be having our third lecture, and we will be discussing complements, number codes and registers, right? So the complement of numbers, these are the bullets which we will be going through, and the complement of numbers we discussed in the last lecture, and I will continue that topic, and then we will be having binary codes, different codes we use for computer system, and then gray codes in ASCII characters, and then a little bit about hardware like storing elements, and then the processing unit. That we will be discussing in today's lecture, right? So whenever we want to represent a negative number on a paper, what normally we do, we put a negative sign or bar at the left hand side of that number. But whenever we have to represent a negative number in a computer system, we have to follow a certain mechanism. So for example, if we have 8 bits to represent a number, so what normally we do, we reserve one most significant bit for the sign, and the rest of the 7 bits are used to represent the number. So if, for example, your 8-bit number, it can represent from 0 to 256, and after reserving 1 bit for the sign, you are left with 7 bits, and now you can represent from 0 to 128, or you can say that total of 128 numbers, right? Whenever you have to represent a negative number in a computer system or in binary number system, you have to follow a certain mechanism. So for example, if you have 8 bits to represent a number, so what you normally do, you reserve 1 bit for the negative sign, and rest of the 7 bits are dedicated for the number. So in this way, the number of unique items you can represent by using this 7-bit number reduces. Mean you have reduced 1 bit, and that 1 bit is actually being used to represent the sign of that number. So instead of 256 unique items in an 8-bit number, you are now left with 128 unique combinations, because we have 7 bits, right? So there are certain requirements for a computer system, so that we can represent the numbers, either they are positive number or they are negative numbers, in a proper way. So let's go through those rules, the requirements. Like 0 is always 0, irrespective of it's a positive or it's a negative. But this is the problem last time we discussed, that whenever we are using ones complement, we have to handle 2 zeros, a 0 with a plus and a 0 with a negative. So this is the drawback of ones complement, right? And we always dedicate the most significant bit for the sign, right? And whenever we take the negative of a negative number, it should be the original number, right? So for example, here if you see, we have minus 55. If we take the negative of minus 55, we get the 55 over here, right? And whenever a number has to be subtracted, like x minus y should give the same result as x plus, and in bracket we have minus y. So what we normally did over here, we take the complement of this y, right, and then by taking the complement, the sign is absorbed by this y, and then we add these two numbers, right. So that is 8 minus 3 should give the same result as 8 plus, and in bracket we have minus 3, right. So here again what we did here, we have taken the complement of 3 minus 3, and the sign is absorbed by that complement, and then we add 8 and the complement of minus 3, and we got the same result. So this is also one of the requirement, right. And whenever we talk about computers, we have to follow these rules in order for proper representation of those numbers. Like in the final bullet, you can see that negative and positive numbers should not be treated differently, right. Whenever we are performing multiplication or we are performing division, right. So let's take an example, right. If we have 8 bits, so we normally have 256 combinations, unique combinations. If we have used those 8 bits, right, and we will start from 0, 0, 0 and 8 zeros, and these are the 8 ones, right. So if we want to represent a negative number using those 8 bits, right, so what normally we do, as we discussed earlier, that we dedicate 1 bit for the sign, and the rest of the 7 bits are used to represent the number. And here again the number of unique combinations, they are reduced, right. So the drawback of this representation, let me show you, right. So here if you have to represent the zeros, right, so these 7 bits are being reserved to represent this 0, right, and this 0 is indicating that this 0 is positive, right. And if we have those 7 zeros and 1 over here, so that indicates a negative 0. So that is the problem with this mechanism to represent the negative number. Like we have to handle a positive 0 and a negative 0, right. So this is the problem. So let's move to the 2's complement, as we have raised certain problems when we used 1's complement, and due to those problems we move to the 2's complement. So whenever we will be calculating the 2's complement of a binary number, right, so we have to perform 2 steps. In the first step, what we will be doing, we will be inverting all the bits of that number, right. So if you look at here, right, so what normally you do, you will invert all those bits, and after inverting or after taking the complement of the corresponding bits, we will add 1 to that number, and that is our 2's complement, right. This is the example. This is the number 12, right, and this is the bit which is reserved for the sign. We will be having examples after a couple of slides. So these are the algorithms, different algorithms, which normally we use in order to compute 2's complement. Regarding the first algorithm, if this is the number whose complement, 2's complement has to be calculated, you will take or invert the corresponding bits, right? So here you have 0 because this is 1, and then we have 1 here because this is 0, and this is 0, we have 1 over here. So we will complement all the bits, and then we will add 1. So this is the 2's complement, right? So if we take the 2's complement of the resultant, so this is interesting what we will get. So this is the number, right, and this is equal to the 2's complement of this number. So we will invert the bits, corresponding bits, and then we will add 1, and we have the resultant, right? So if you compare this with this, they are the same. So it means if you take the complement of a number and 2's complement of a number, and you take the 2's complement of the resultant, you will get the original number, right? So these are the ranges, right? If we have a number n, right, and in that number we have smaller n number of bits, then we can represent 2 raised to power n minus 1 with positive sign, right, and 2 raised to power n minus 1 with negative sign. So this is the range, right? So if you have 8 bits, right, and 1 bit is reserved for the sign, so you can calculate the total number of possible combinations, right, from 0 to 127, and then from 0 to minus 127. So these are the possible combinations, or you can say this is the range, right? Okay, so let's have examples if we have to perform addition by using 1's complement, right? So we have the two numbers that has to be added. So this is 12, and because this is positive, so we have 0 over here, and this is 1, and we have 0 over here. So we will straight away add those numbers, and if there is no carry, right, so we will add the carry here, because no carry, so 0, so we will get the same result. So 12 plus 1, 13, if we take it as decimals, but in binary we have 0, this is for sign bit, and 1, 1, 1, so 1 plus 4, 5, and plus 8, 13. So this is the addition using 1's complement. Now let's talk about subtraction using 1's complement, right? So we have two numbers that has to be subtracted, right? So this is 12, and this is minus 1. So the number that has to be subtracted, or that is having the negative sign, we will take the complement of that number, 1's complement, right? So this is the number, and minus, so due to minus we will take 1's complement of that number. So this one is for sign, because sign is negative, and we have inverted all the bits, because this is 1, so we have placed 0 over here, and this is 0, so we have replaced 1 here, so we will complement all the bits, right? So here after the complement, the sign is absorbed by this number, and we will straight away put this number over here. So after the ones complement, sign is absorbed by this number, and we will straight away place this number over here, and we will add those numbers, right? So this is the resultant, right? And we have a carry here, so we will place that carry here, and we will add that carry. So this is the final result. So look that we have a 0 in the sign bit, so this means the resultant is positive. And if we think in the decimal number systems, so we straight away will realize that 12 minus 1 is equal to plus 11, right? So this is the subtraction using ones complement, right? So now come to the additional operation using twos complement, right? So if the two numbers have the same sign, right, like they are positive, what we will do, we will straight away numbers in the binary format. This is the sign bit, and this is the second number that has to be added. So this is the sign bit, right? And we will have the resultant over here, and this is the sign bit. If there is a carry, what normally we do, we ignore that carry, right? So this is the addition using twos complement, right? And the two numbers that has to be added, they have the same sign. So here we have the positive numbers. So let's move to the subtraction using twos complement. So 12, we converted that 12 to the binary, equivalent binary, right? And this is minus 1, so minus, so this is the binary of 1. So the negative number, we will take the twos complement of that number. So this is, we will invert those numbers, right? 0, 1, 1 and 1. So this is ones complement, and then we will add 1, so we will get 1, 1, 1 over here, which is the same, right? So then you will place the numbers. This is 12, sign bit is 0, and this is minus 1, and after taking twos complement, the sign is absorbed by this number. So we will add those numbers, right? And this is the sign bit, and this is the carry. So we will ignore the carry, and we will get the resultant. This is the sign bit, and this is the resultant. 1 plus 2, 3, and 3 plus 8, 11. So this is 11, and the sign is positive. So it means if we think in a decimal way, right, so we will straight away come to know that 12 minus 1 is equal to 11, right? So this is another example, subtraction using twos complement. We have two numbers, 13, and we have to subtract it from 5, right? So we will convert 13 to equivalent binary number, which is this, and then we will convert 5 to binary, right? So this is the negative sign. So as a result of this negative, we have to take the twos complement of this negative number, so that the sign will be absorbed. So this is the twos complement of this negative number, and then what we will do, we will add these two numbers. So this is 13, 0 is indicating that it has a positive sign, and this is 5, but 2's complement of minus 5, and 1 is indicating that it is a negative number. We will add those numbers, and what normally we do, we ignore the carry. So 0 is indicating that this is the positive, so resultant has to be positive, and we have to ignore this carry. So this is 8, right? So another example, right? So we have minus 12, 5. So we will convert that 12 to equivalent binary, and we place the negative sign over here, and this is the equivalent binary of 5, and this is the positive sign. So because this number is negative, so we have to take the 2's complement of that number so that the sign is absorbed by the 2's complement, right? So this is the 2's complement of minus 12, and this is the binary equivalent of 5. So we can see that this 0 is showing the positive sign, right? So we will place those numbers, right? So this is 5, and this is 2's complement of 12. So we add those numbers, right? So 1, 0 and 0, 0. So 0, we will have a carry over here, right? So 1 plus 0, 1, and 0 plus 1, 1. So this is the sign bit, and this is 1. So this is indicating that the resultant is negative. So what we will be having as a resultant, right? So this is the way out how we handle the subtraction, right? Right. So that's all about complements and different operations like addition, subtraction using those complements. But one thing I have to mention that one's complement is rarely being used in today's computer system due to their disadvantages, I must say. But 2's complement is heavily used in current generation computer systems due to their advantages. Like one of the advantage is that we have to handle only 1 0, right? And you have to perform fewer operations whenever you are performing addition, subtraction as compared to the 1's complement. So these are the advantages when we perform arithmetic operations in computer systems and using 2's complement, right? So let's move to the next topic, that is codes. Let me introduce the data representation and the communication. When we think about human communication, we use language, different languages, and those languages, they have different grammatical restrictions, right? We have different dialects, gestures, and we also use images and sounds. But whenever we talk about computers, we should devise or design codes in an effective and efficient way, because we have to store the information, store the data, right, in the binary format, and that data can be stored, right, in the binary format if the computer and the input device, they know each other, that what is being sent, and the computer know what I have received, right? And then when you after storing that data, you have to process that information, that data, in order to extract the useful information, right? So this is the snapshot of the conversion, that how the data is converted, right? So here we have the input device, and we have the computer over here, and you can see that if we have pressed this combination from the keyboard, then this input buffer will receive this data, and this data will be sent to the computer and will be stored there in binary format. If the computer don't have the ability to understand this data, then this information is useless for us. So it means there should be a standardized mechanism, or there should be some standardized coding scheme, so that the input device and the computer, they can understand each other, right? Okay. So as our computer system is based on binary number, so numbers are important in computer because they represent the information in a precise way, and then that information has to be stored somewhere, and ultimately that binary numbers or binary data has to be processed in order to extract the useful information from that data, right? So let's start from the binary coded decimal, right? So in that coding scheme, we represent each number with a 4-bit binary equivalent, right? So here if you take the example, right, so if you take the decimal equivalent of those numbers, right, so this is 3, and this is 2, and this is 9. So we will place 10 because this is the base 10, but this is not the same when we talk about BCD, binary coded decimal, right? So these are the digits. We have 0 to 9, right? And these are the bit patterns, right? And you might have noticed that, right? So let's start with the binary coded decimal, right? So in that coding scheme, we represent each decimal digit with 4 bits, right? So if you take the example of this number, right, so we have 3 different 4-bit combinations. So this is equivalent to 3 decimal, this is equivalent to 2, and this is equivalent to decimal 9, right? So if you talk about this combination, right, so this is not the same, right? And this is the table mentioning this binary code. We have digit 0, then 1 and 2, and so on and so forth, and we reach till 9. And these are the 6 patterns that are not used, they are excluded from this BCD, right? So if you put all the things together, because we know the binary, right, and we know the octal, and we also know the hexadecimal. So here you can see that after the 9 we will start representing those BCDs in a different way. Like here, if we have decimal 10, we will represent the 1 0 0 0 1 and this 0 as 4 0 bits, and this is the 1 1. So this is 1 and this is 1. So each number has to be represented in a 4-bit code. So this is a coding scheme. This is a coding scheme, right? But there are certain problems that are affiliated with this binary code, binary coded decimal, and they are not very efficient. You can see that even we have to represent this 11, right, in this way, and we are using 8 bits or consuming 8 bits. There are certain problems that are associated with this binary code, like though they are being used in computers in 40s and 50s, like they are not efficient. If you look at, you have to represent this 11, you have to consume 8 bits to represent this 11, right? Though if you look at the binary, you can represent this 11 with these 4 bits, right? And so this is the disadvantage regarding the binary coded decimal. Then we have the gray codes. So this is not a number system, right? As this is misconfused or misunderstood, that this is a sort of number system. So this is not a number system. So if we look at the digit, this is the decimal, this is the equivalent binary, and we have the corresponding gray code, right? If you move to 1, and you will notice that only 1 bit has been changed. This is 0 and this is 1. And then if you look at the 2, so this one remains the same and this bit has been changed. So 1 bit change when we move from one decimal to the other, right? So this is useful for reducing errors in communication. Like you can see that only 1 bit is changed, right? And one of the advantage of this code is this is a scalable. You can scale this code for larger numbers, right? So this is the gray code. And now let's talk about ASCII. That stands for American Standard Code for Information Interchange. So this is a 7-bit code, and the 8-bit is reserved for error detection, right? So actually our keyboard is based on this ASCII code, right? So these are the codes, right? So this is the most significant bit and this is the least significant bit, right? For example, if you have to represent A, so how you will be representing this, right? If you look back, so this is the most significant, so it means this will be the most significant part and this will be the least significant part. So we will be having 1 1 0 and 0 0 0 1 when we are representing A by this ASCII code. So these are the alphabets, these are the capitals, and these are the small letters and their codes. For example, if you want to represent a capital P, what you will be having, 1 0 1 and we will be have tetra 0, right? And if you have to represent small p, right, so we will be having 1 1 1 and then tetra 4. So this is alphabets, right? And this is the numeric codes, right? If you have to represent 5, so we will have 0, 1, 1, and this is the 5, right? And these are the punctuations, right? So the ASCII codes, they are very useful for data transmission, right? ASCII, maybe you have listened about the Morse code when in the early days of communication over wires, copper wires, we have Morse codes, right? So ASCII codes, they are more immune to noise, right? And this is the transmission rate, right? And you might remember when we have the dial-up connections a couple of years back, we normally come across this number, 56.5 kbps, right? So now, but now we have DSL and some advanced sort of equipment, and we are having bandwidth capability or capacity in megas or and more, right? So whenever you talk about data transmission, right, and you have to send a certain amount of data from one part of the computer to another part of the computer, or from one register of the computer to another register, or to another unit in the computer, or maybe if there are some small wires they are involved in between, so there are chances that the data might be corrupted, or there can be some noise that can corrupt the data. So to avoid this errors, what normally we do, we use parity codes, right? So what we do, we concatenate or associate a parity bit, right, to that data, right? So there are two sort of different parity codes. One is odd and the other is even, right? So in the even parity bit or even parity code, what you have to do, you have to count the number of ones. If the number of ones are odd, so this is the bit that is reserved for the parity code, parity check. So the number of ones are odd, and your system know that we are using even parity. So what you will do, you will place a 1 over here in order to make the total number of ones even, right? So this is the information bit, right? And this is the bit reserved for parity. So similarly, when you are using odd parity, right, so you will count the number of ones. If the number of ones are odd, we will place a 0 over here, and if, for example, if we have 1 over here, so the number of ones will be even, and we have to place a 1 over here. So this is the way out how you use those parity codes. So normally we place those parity codes with the ASCII characters. So here we have 0. So this is the way out how you use parity codes. So here we have a table, character and ASCII, equivalent ASCII of that character, and then we have odd parity and the same ASCII with even parity, right? So this is a way out how you use parity code in order to make your data susceptible to noise, right? So we have a table over here, right? So we have a character here. This is the ASCII equivalent, right? And here in this column we are using the odd parity, and in this column we are using the even parity, right? So this is the ASCII equivalent of this character, right? And you know that we have even number of ones, but we have used odd parity here. So in that ASCII equivalent we have even number of ones, so to make them odd we will place a 1 over here, and the same ASCII number, so we have the even number of ones, so we will place a 0 over here when we talk about even parity, right? So this is another character X, and this is the ASCII equivalent of that character, right? And this is the odd parity. So number of ones, they are already odd, so we will place a 0 over here. But when we are using even parity, the number of ones are odd, and to make them even we will place a 1 over here. So on the receiver side, what will happen on the receiver side? For example, you have pressed this key from your keyboard, and your system has some sort of error. There is some noise in the buffer, or maybe due to some other problems. So the system will detect, right? If your system know that we are using odd parity, and the receiver side will count the number of ones, right? So if they are odd, right, and because this is the original data and the number of ones has to be counted over here, right? And if a 0 is here, so it means the number of ones, right, they are odd, right? We are using odd parity, right? So in the even parity, the receiver side know that we are using the odd parity, even parity, and the number of ones, total number of ones should be even, right? And if there is due to some error, one of the bit has been changed, so the number of ones will be odd, but we are using even parity. So in this way the system can detect that there is an error, and it can request to resend the data again, or there can be some other mechanism to correct this error, right? So this is the way out how, but there can be a problem, right, which cannot be detected, which is not detectable. This is the number X, right, and this is the equivalent ASCII character, ASCII number, binary number, and this is the odd parity, right? So the number of ones, they are already odd, so we will place a 0 over here, and when we talk about even parity, we will place a 1 to make the total number of ones even, right? So this is the equal sign, right? So the number of ones in the ASCII, right, 4. So in odd parity we have to place a 1 to make them odd, because we are talking about odd parity over here, and here we have to place a 0 because the number of ones are already even. So whenever we are talking about data transmission, we have a sender and a receiver. For example, keyboard is your sender and the computer is your receiver, right? Or the buffer of your computer system is your receiver. So when you press this key from the keyboard and you are using odd parity, what your system will do, it will compute the number of ones, and they should be odd because we are using odd parity. And if due to some problem this 0 have become 1, so now the total number of ones are even, but we are using odd parity. So the system will detect an error and it can adopt the mechanism to rectify this error. So, and when we talk about the even parity, so take the same example of keyboard and the buffer of your computer system. You pressed this equal sign from your keyboard, and the buffer of your computer system, it received, for example, this 0 has been changed to 1 due to some problem. So now we have the total number of ones, they are odd, but we are using even parity. So the system will detect the error and will take the necessary action to rectify this error, right? So after talking about those different coding schemes, let's talk about the storage, right? So because in our computer system we have to store the data in order to process that data or maybe for future use, right? So we need binary cells to store the data, and when we combine those different binary cells, we call them a register, right? So the data in those registers, they are being stored by using different values. We can use hexadecimal values, we can use binary coded decimal, or we can use ASCII, right? So here we have a register, and each slot in that register is a binary cell, and we can store the data in that register, right? So this is how we transfer data, right? So this is your logic circuit. It can be, for example, you can say this can be an adder, and these are the register to store two different numbers, and what you have to do, you have to add those numbers A and B, and the resultant has to be stored in register C. So this is about data transfer between different registers, right? So you can move data from one register to another register, right? And normally we move data or store data for processing, right? If, for example, we have an adder here, this is the adder, right? And this is the number 1, this is the another number 2, or you can say, and number 1 is stored in register B, and number 2 is stored in register A, and we have the resultant after the addition, right, over here in register C. So this number and this number has to be added by this adder, right? So this is a sort of, we are processing the data, and then we will have the resultant over here. So this is how we transfer data from one register or to the other, or maybe process data and then move to different registers. So this is a snapshot of transfer of information. For example, you have a keyboard, this is the control unit, right? And this is the processing unit, and you have to store the data somewhere, right, for future use, right? So you press J, right, and then you press O, then you press H and N. So this control unit know which key has been pressed, right? When J is pressed, it will send the corresponding ASCII, and this register will send this data to the processing unit, and this will move to the left, right? Then when you press O, this register will receive this O, and then this will be received here, and this, after each reception, right, the data will be moved one step to the left. Right? So we have a shift register here, right, and this data has to be stored over here, right? So this is the memory register, and this is the, you can say, processing, because we are storing the data and we are shifting the data, and this is the input unit. So this is the transfer of information when we talk about computer system, right? So this is, if you think about a little computer, right, we have a processing unit over here, right? This is the memory unit, right? So if you have the two numbers that are being stored over here, number 1 is here, and this is the second number, right? And you want to add those numbers, right? So this is the operand 1, this will be loaded into this register R2, and this is the operand 2, this will be loaded into register R1 in processing unit, because this is the brain of your computer, and this is the main adder circuit. So this adder will add these two numbers, and we have the resultant over here, and then this resultant is stored in the memory unit over here. So to build a computer system, we need a mechanism for storage memory unit, right? And then you need a processing unit, right? I mean the brain, and then you have to communicate the data between different units. So here we are transferring data from the memory unit to the central processing unit. So this is the example of a very precise computer, little computer. So that's all for today's lecture. So today we have continued our complements, right? And then we talk about different coding schemes, right? And we talk about registers. So that's all for today's lecture, and मेरी तरफ से आपको अल्लाह हाफ़िज़। अपना, अपने दोस्तों का, अपने रिश्तेदारों का और गिरद नवाह के लोगों का ख्याल रखिएगा। अल्लाह हाफ़िज़। अस्सलाम वालेकुम।